All right, everybody, welcome back for our next lecture video here. So we left off here talking about entropy and doing a bunch of stuff regarding that and talking about catalysts and reaction rate, all that good stuff here, reaction rate, collision theory. Now, this is going to all be stuff that's going to help us transition into exactly what equilibrium is. Now, what is equilibrium? Well, we kind of talked about it in class not too long ago, but equilibrium is almost like a tug of war, right? Generally speaking, when you guys play tug of war, unless the sides are totally uneven, you've got some really even sides, right? Tug of war is not going to really, no one side is going to win. So you've got, one side really tugging hard, but they're not really going to win and push them over the line, versus the other side who's also tugging really hard as much as they can, and they're also not winning and pushing the other team to the other side either, right? So both teams are pulling on the rope, but the rope is not moving. That is essentially what happens in these equilibrium situations here, okay? So in chemistry, not all reactions proceed in one direction, right? Up until this point, guys, a lot of what we've seen in this class of chemistry, whenever we've seen chemical equations, they've all been one-sided, right? It's that one-sided arrow where an arrow is just kind of pointing in one direction only. But in reality, guys, a lot of different reactions in chemistry are actually reversible, which means the products that the reactants you're using to form products can also turn around and have those products in turn move reverse and form more reactants. Okay, so for example, a reaction between NO2 gas and N2O4 gas. These substances can constantly move back and forth, resulting in a reversible reaction where NO2 is constantly forming N2O4 and N2O4 is constantly going in the reverse direction with, in the reverse direction to form more NO2. Now, what it's all based on, guys, is this guy right here, right? This double-sided arrow. We saw it once a while ago, and we're seeing it crop back up again, and we're going to use it a lot this remaining part of the chapter. Okay, so lock in for that. So now, the forward reaction occurring in this example here is exactly kind of how you see it, right? It's NO2 gas forming N2O4 gas, right? One arrow, one direction, that's it. But the reverse reaction is exactly what you might, assume that it is, right? It's the opposite, right? It's N2O4 going in reverse, forming NO2 gas. But the thing is, guys, those are happening at the exact same time. So in the exact same vessel or whatever, NO2 is constantly forming N2O4, and that N2O4 is constantly going in the reverse direction to form more NO2. Okay, so that's essentially what's happening in equilibrium. But in terms of concentration and time and always looking at graphs and whatnot, what actually is happening at equilibrium? Well, for example, the rate at which the forward reaction is occurring is going to always be equal to the rate at which the reverse reaction is occurring, right? So those things are going to happen at the exact same rate at the exact same time. But the thing is, guys, the concentration of these reactants and products is going to end up staying constant. It does not change, right? If things stay constant, that means they're unchanging and do not change. So this little graph here, guys, is a graph that's plotting time of a reaction occurring versus the concentration of those substances. Notice how, I'm going to get my little marker out here. Notice how you've got H2 gas and N2 gas, right? The concentration of these guys start much higher than our product, which in this case here is NH3, right? It actually is going to start out way at the bottom there at a concentration of essentially 0, right? Because at time 0, your reactants, your H2 and N2, have not yet collided, right? Adding to that collision theory we talked about in class the other day. They've not yet collided together to start forming and reacting into products. Well, as that happens, as those collisions occur, the concentration of your H2 is going to slowly go down. The concentration of your N2 is going to slowly also go down. And eventually, as those two's concentration are going to slowly go down, that was a horrible line there, as the two concentrations of H2 and N2 slowly go down, at the same time as they go down, NH3 is constantly being formed. And the concentration of which that NH3 is forming is going to constantly go up. And then there's a certain point, guys, where the concentrations end up, and I'm doing a horrible job with these tracings here, the concentrations of them essentially hit a breaking point. where they constantly end up being unchanging or constant, right? And that's represented by this dotted line here. At this point on, guys, the concentration of H2N2 as reactants is totally going to be constant, as well as the concentration of NH3, right? The flat line there represents an unchanging y-axis, which means the concentration of them will not change even as we progress down the x-axis, which is time in this case here, okay? That's essentially what's happening. And again, it essentially looks like nothing is happening in this reaction because those concentrations of your substances are unchanging and constant, okay? And this is your example here, right? Now, this is a little bit of a different graph that looks kind of similar to this, but is different, right? Notice how the x-axis for this graph is time, and it's still time for this, but the y-axis for this graph was concentration, and now for this graph, it's rate, okay? Rate of reaction. So what you see is, as the forward reaction starts to occur, the rate at which it happens starts to slowly decrease as time progresses. And then the rate of the reverse reaction starts to increase drastically and eventually level out at a certain level. And then that's when the purple line forms here, and we have reached equilibrium, where the rate of the forward reaction equals the rate of the reverse reaction, and they're constantly happening at the exact same rate, at the exact same time as you progress through the reaction. Now, let's take a look at this graph here, kind of concentrating on what I was showing you a couple of slides ago, right? Initially, all you have are your reactants, H2 and N2, right? All you have is hydrogen and nitrogen. They have not yet officially collided and formed our products yet. So there is no NH3 at all yet. Now, as the reaction occurs, there's going to start to be a little bit of a change in the concentration of these substances, right? H2 and N2's concentration are going to go down, whereas the concentration of our NH3 is going to go up. Eventually, at equilibrium, the dotted line right there, the dotted vertical line there, is equilibrium, which means that all of these substances are going to be constant in terms of their concentration. Now, a couple of things in terms of what's not happening at equilibrium. The amount of concentration of the reactants is not necessarily going to be the same as the amount or concentration of the products, right? Again, so what I'm saying is your reactant concentration is not going to equal to your product concentration, because we can see that very clearly here, right? Although they're constant, that does not mean that they are equal, right? H2 is a little bit higher, N2 is a little bit lower than that, and NH3 is a little bit lower than that, and N2 is much lower than that, right? They're all at different levels of concentration, but again, that does not mean that they're not equal. It just means, or it means they're not equal, but not necessarily constant here. Or this can be true, but it's not usually. Sometimes they are going to be equal and constant, but again, both the concentration of the reactants and the products, the concentration of the products are constant, but not equal. So just like in tug of war at equilibrium, there can be different number of people on each team, but the number of people on each team remains the same. Okay, there can be different number of people on each different team, but again, the number of people on each team is going to remain the same. Now, what happens as a reaction approaches equilibrium? We're going to see these four different pictures here. And sort of progress through this reaction of nitrogen gas and hydrogen gas. So at A, we've got N2 and H2 reacting to begin forming your NH3. At B, both the forward reaction and the reverse reaction are occurring, but the forward reaction is occurring at a much greater rate because you've got a lot more N2 and H2 abundantly available in that case there. Both C and D are going to be where you've got and finally have reached your equilibrium. The forward and reverse reactions are occurring at the exact same rate here. Now, that's a lot of text, but let's just kind of look at these pictures individually here, right? In this picture here, picture A, all you have is a bunch of these N2 molecules here, which are these larger light blue molecules, and this H2, which are these smaller, like purplish looking H2 molecules, right? They've not yet officially collided. That's slide A here. Now, once any of these two N2s or H2s have officially collided with each other, that is when you have a reaction starting to occur. And that reaction has NH3 starting to form. So we've got a couple of NH3 particles right here. We've got one right here. Oop, slide one backwards. Let's try it again. We've got one right here. Here, NH3 over here, NH3 over here, and an NH3 over here. But again, outside of these four particles, guys, the rest of them are still a bunch of N2s and H2s. There's still a ton of those reactants that have not yet formed products. But even though those reactants, nitrogen and hydrogen, are forming more NH3, ammonia, that does not mean that these 4 little guys here are not going to start forming more reactants again, going the reverse direction, which is exactly what ends up happening here, right? So as we progress through this reaction, we're going to see more and more of these NH3 molecules cropping up. And although those are forming at a faster rate, once you've hit equilibrium, all you have is a very, very even distribution, an even constant, exchange of creating products and creating reactants, kind of going back and forth, in the forward and the reverse direction. Okay, and that's the end of the video. So I'll see you guys in class next with some example problems.